History is not the straight line we were taught. Our journey through 30 mechanical artifacts from antiquity will reveal a startling truth about technological progress. You will see human ingenuity not as a steady climb, but as a story of brilliant flashes and profound forgetting. How could a 2,000-year-old device perform calculations rivaling an 18th century clock? What does a simple clay jar have to do with the invention of the battery? By the end, your understanding of the past will be permanently reshaped. What does it say about us when the most advanced ideas can simply vanish? That corroded lump from the seafloor was the Antikythera Mechanism. For decades it sat in a museum drawer, a curiosity no one could decipher. Then, researchers using modern X-ray technology peered inside, and the true marvel was revealed. This was not a simple navigational tool. It was a miniature cosmos of bronze, a clockwork universe built by hand over 2,000 years ago. Its intricate system of at least 30 interlocking gears could model the erratic motions of the moon, predict solar eclipses, and even track the cycle of the ancient Olympic Games. It was, in essence, a mechanical computer programmed with the astronomical knowledge of its age. The sophistication is staggering. As historian Derek de Solla Price observed, finding such a device from this period is like discovering a jet engine in the tomb of King Tut. It represents a pinnacle of Hellenistic engineering that simply should not exist according to our conventional timelines. This one artifact forces a difficult question. If the ancient Greeks could build something this precise, this conceptually advanced, what happened to that knowledge? The mechanism hints at a vibrant tradition of mechanical arts, a school of thought and craftsmanship that flourished and then was utterly extinguished. Its silent gears speak of a forgotten chapter in human ingenuity, a technological peak that was not surpassed for well over 1,000 years. This was not a gradual improvement. It was a flash of genius followed by a long, dark silence, and as we leave the waters of the Aegean, another artifact from a different ancient culture whispers a similar, electrifying secret. That long silence was not empty. It was punctuated by other, quieter sparks of understanding in distant corners of the ancient world. In the 1930s, during a routine railway construction project near Baghdad, workers unearthed a collection of rather ordinary-looking clay jars. One in particular stood out to the director of the Iraq Museum, Wilhelm Koenig. It was a simple vessel about the size of a man's hand, but its contents were curiously deliberate. Inside, a copper cylinder had been carefully fitted, and within that cylinder sat an iron rod. The whole assembly was sealed at the top with a layer of asphalt, a perfect insulator. When Koenig examined it, a startling hypothesis formed in his mind. This was not a container for scrolls or spices. It was, in all its unassuming simplicity, a battery. Dating from the Parthian period, sometime between 250 years before the Common Era and 224 years of the Common Era, this artifact, now known as the Baghdad Battery, presents a quiet but profound mystery. If you were to fill such a jar with an acidic liquid, something as common as vinegar or fermented grape juice, a chemical reaction would occur between the two different metals. Electrons would flow from the iron rod to the copper cylinder through the acidic solution, creating a small but measurable electric current. Modern experiments have shown a single cell like this can produce around 1.5 to 2 volts of electricity. That is not enough to power a light, of course, but it is far from nothing. So what was it for? The leading theory among some researchers is electroplating, the process of using electricity to bond a thin layer of a precious metal, like gold, onto the surface of a less valuable object. Numerous artifacts from the same region and era show fine gold plating that experts have struggled to explain with known chemical techniques of the time. Could a bank of these simple clay jars, wired in series, have provided the gentle, consistent current needed for such delicate work. Other suggestions point to its possible use in medicine, perhaps for the mild, tingling sensation we now associate with electrotherapy, a way to soothe aching muscles. The truth is, we may never know its exact purpose with absolute certainty, and that is precisely the point. The existence of this device is not about proving the Parthians had a national grid. It is evidence of a fleeting, localized grasp of a fundamental force of nature, centuries before Alessandro Volta would officially invent the voltaic pile in 1800. It represents an idea that flickered into existence, was used for a specific, perhaps narrowly understood purpose, and then was forgotten, its principles lying dormant for over a millennium. This pattern of isolated genius, of technological insights blooming in one valley only to wither without spreading, forces us to reconsider the very geography of innovation. Our search for these scattered sparks of ancient genius now turns to an empire renowned not for hidden currents, but for breathtaking, visible precision. The quiet ingenuity of the Baghdad Battery gives way to a monument of staggering, silent endurance. In a courtyard in Delhi, a single piece of forged iron has stood exposed to the elements for over 1,600 years. It is not a relic sheltered in a museum case. It faces monsoon rains, punishing humidity, and modern pollution, yet it shows almost no sign of the rust that should have consumed it centuries ago. This is the Iron Pillar of Delhi, a 7-ton, 23-foot-tall column erected in the 4th century of the Common Era, and it represents a metallurgical mystery that challenges our assumptions about ancient technology. Modern science can explain the pillar's resistance, but only after careful study, and the explanation reveals how advanced that ancient craftsmanship truly was. The pillar was forged from a single, massive piece of wrought iron with a remarkably pure composition. Its secret lies in what it contains and what it does not. The iron has an unusually high phosphorus content and a very low sulfur content. This precise imbalance, likely accidental from the ores and charcoal used by the ancient smiths, triggers a beautiful accident of chemistry. Over time, the phosphorus helps form a thin, protective film of iron hydrogen phosphate on the pillar's surface. This film is stable, adherent, and self-repairing. When the humid air or rain touches it, the film does not flake away as rust would. It instead bonds more tightly to the metal beneath, creating a brilliant, invisible shield. This process, called passivation, is a principle we in the West only began to understand and intentionally apply during the Industrial Age. For the craftsmen of the Gupta Empire, this was not a theoretical science. It was an empirical art, a hard-won knowledge gained through generations of trial, observation, and skill at the forge. They may not have known the molecular reasons, but they knew how to produce iron that lasted. The pillar itself is an inscription, a declaration in both word and material. Its Sanskrit verses glorify the valor of King Chandragupta II, but its very existence glorifies the mastery of its makers. It stands as a direct contradiction to the idea that corrosion-resistant iron was a purely modern achievement. Here was a technology so advanced for its time that it seems to have been a pinnacle rather than a stepping stone. The knowledge was so specialized, so tied to specific materials and artisan traditions, that it did not spread or systematically evolve. It was a brilliant, localized peak that later cultures could not easily replicate. This pattern of a towering achievement followed by silence now shifts scale, from a monumental column that defies the atmosphere to a small, intricate device that seems to defy the very passage of time itself. While the iron pillar stands as a defiant monument, another Roman artifact whispers its mystery from the palm of your hand. Scattered across the former empire from Britain to Hungary, over 100 small, hollow bronze objects have been unearthed, each one a geometric puzzle. They are known as Roman dodecahedrons, and they are perhaps the most beautifully frustrating enigmas left to us by antiquity. Each one is a 12-sided form, every face a perfect pentagon, and at the center of each face is a circular hole, each hole a different diameter. They range from the size of a golf ball to that of a large grapefruit, often adorned with small knobs at each corner. They date from the 2nd to the 4th centuries of the Common Era, and despite their numbers, not a single scrap of Roman text, no inventory, no letter, no manual mentions them at all. Their silence is absolute. This complete absence of documentation has sparked a century of scholarly debate and public fascination. What were they for? The theories are as varied as the holes in their faces. Some suggest they were practical gauges, used by engineers to calibrate the standard sizes of water pipes, or by military quartermasters to measure the diameter of stone projectiles for catapults. Others propose they were tools for knitting, the knobs used to create the fingers of gloves. There are astronomical theories that they were instruments for calculating the optimal sowing dates by measuring the angle of sunlight. And still others see them as objects of ritual, perhaps used in ceremonies or as symbols of status and knowledge. Yet each theory stumbles on the evidence of the objects themselves. Most show little to no wear marks from repeated use. Their sizes and decorations vary significantly from one to the next, arguing against a standardized, empire-wide tool for a common task. If they were for knitting, why are they found in regions with different climates? If they were for the military, why are they often found far from frontier forts? Their very design seems to deliberately resist a single, obvious purpose. This is their profound lesson. The Roman dodecahedron challenges our comfortable assumption that we understand the practical, everyday world of a civilization as documented as Rome's. It is a stark reminder that the past is filled with ordinary objects whose functions were so ingrained, so culturally specific, that no one thought to write them down. They were simply part of the fabric of life, a technology of the everyday that evaporated when that culture transformed. Their mystery forces us to confront the limits of our archaeological imagination. We can reconstruct aqueducts and roads, but we may forever be guessing at the purpose of a peculiar bronze shape that a Roman artisan crafted with such care, held in their hands, and understood completely. This puzzle of a forgotten tool's function finds a fascinating contrast in our next artifact, where the purpose is gloriously clear, but the engineering precision required to achieve it leaves us just as awestruck. The quiet precision of a portable timekeeper speaks of an empire built not just on conquest, but on the meticulous organization of daily life. In the ruins of Ai-Khanum, a Greek city founded in the far eastern reaches of modern-day Afghanistan, archaeologists found a small bronze disc no larger than the palm of your hand. At first glance, it might be mistaken for a piece of ornate jewelry or a decorative plate. But this object, dating to the 3rd century before the Common Era, is a masterpiece of miniaturized engineering, a portable sundial of breathtaking complexity. This was not a simple stationary marker for a courtyard. This was a traveler's companion, a personal device designed to tell the hour with remarkable accuracy across the vast span of the Hellenistic world. Its face is a dense web of finely engraved lines and curves, a permanent map of the sun's path through the year. It featured adjustable components, likely a gnomon or shadow caster, that could be set for the specific latitude of the user and the current date. With these adjustments made, one could simply hold the disk level in the sunlight, and the shadow would fall across a series of concentric hour lines, revealing the local time. Even more astonishing, some of these portable dials contained multiple city names engraved around their edges, cities like Alexandria, Rome, or Babylon. This meant a merchant or an official moving across the empire could, in theory, recalibrate the device to tell the time not just where he stood, but in another major city hundreds of miles away. Think of that for a moment. In an age before mechanical clocks, this was a pocket-sized computer running on solar power, its programming etched permanently in bronze. It applied advanced principles of geometry and spherical astronomy to solve a very human problem: the need to coordinate activities, meetings, or rituals across great distances. The artifact from Ai Khanum reveals a society where sophisticated knowledge was not locked in temples or royal courts. It was diffused to the very edges of the known world, a tool for administration, trade, and scientific inquiry. This level of portable, applied mechanics represents a peak of practical innovation that would not be seen again until the Renaissance, over 1,000 years later. It shows a civilization thinking not just on the grand scale of monuments, but on the intimate scale of the individual's day. Yet for all its cleverness, this technology relied on the consistent presence of the sun. Our next discovery reveals a civilization that looked beyond the daylight, seeking to capture and control a far more unpredictable and powerful force of nature. That mastery of hydraulics for portable timekeeping was just the beginning. In the rolling hills of southern France, near the town of Arles, lie the silent ruins of an ancient industrial giant. This is the Barbegal aqueduct and mill complex, and when it was operational in the 2nd century of the Common Era, it was not just a mill. It was a flour factory of staggering scale, a testament to Roman engineering that feels shockingly modern in its ambition. Picture a steep hillside transformed into a mechanical cascade. An aqueduct brought water from miles away to the top of the site, where it was then split into 2 separate channels. These channels each fed a row of 8 massive water wheels, arranged in a breathtaking, descending staircase down the slope. 16 wheels in total, each one likely over 6 feet in diameter, all turning in a synchronized, thunderous rhythm. This was a gravity-fed system of brilliant efficiency. As water poured onto the top wheel, making it an overshot wheel for maximum power, it then spilled into a trough that directed it onto the next wheel down, and then the next, harnessing the same water again and again. The gears from these wheels turned heavy millstones, grinding grain into flour with relentless, automated force. Historians estimate this complex could produce around 4.5 tons of flour every single day. That is enough bread to feed the entire population of nearby Arles, a city of thousands, with surplus likely shipped to other parts of the empire. This scale of production is not merely impressive, it is revolutionary. It represents a degree of mechanical industrialization, of systematized mass production powered by renewable energy, that we do not see again on such an organized scale until the watermills of the European Middle Ages, nearly 1,000 years later. The Barbegal complex shatters the simplistic image of the ancient world as one powered solely by human sweat and animal muscle. Here was a society that understood and deployed water power not for a single task, but for integrated, large-scale industry. It was a localized industrial revolution, a concentration of knowledge, resources, and engineering that flourished in one specific region under the stable conditions of the empire. And that is the crucial, haunting lesson of Barbegal. Its existence was fragile. This technology was not widespread common knowledge. It was a pinnacle achievement dependent on the complex infrastructure, specialized engineers, and economic stability that the Roman Empire provided in its prime. As the empire's cohesion fractured in the centuries that followed, the expertise to maintain, let alone replicate, such a vast and intricate system fragmented and faded. The knowledge of how to orchestrate 16 water wheels into a single flour-producing machine was lost, and the industrial hum of Barbegal fell silent for centuries. This vision of water harnessed for large-scale, practical work finds a stunning contrast in our next discovery, where water was channeled not for sustenance, but for spectacle and illusion on a truly imperial scale. The industrial thunder of Barbegal's water wheels gave way to a more delicate symphony in the heart of Alexandria. Here, in the 3rd century before the Common Era, an inventor named Ctesibius achieved something that feels almost magical. He transformed the simple water clock, or Clepsydra, from a dripping bowl into a breathtaking mechanical theater. His device was not merely about measuring hours, it was about announcing them with spectacle and scientific wonder. Imagine a public square where citizens gathered not just to check the time, but to watch a performance engineered by water itself. Ctesibius solved the fundamental flaw of earlier water clocks, where the flow slows as the reservoir empties. He engineered a system to maintain a perfectly constant water pressure, likely using a clever overflow tank and a precision valve. This steady stream turned a water wheel or floated a rising indicator with unwavering regularity. But the genius did not stop there. This constant flow was harnessed by a train of gears. These gears did not just move a hand on a dial. They animated small figurines, perhaps causing a bird to sing, a figure to strike a bell, or even whole scenes from mythology to play out as the day progressed. It was automata, powered by hydraulics and governed by feedback control, centuries before the term would be coined. The Roman architect Vitruvius, writing about such clocks later, detailed the painstaking calibration required, the precise ratios of gear teeth to water flow, revealing a deep, theoretical grasp of both fluid dynamics and mechanical systems. This was more than a timepiece, it was a public demonstration of humanity's growing command over the natural world, a fusion of art, science, and civic life. The loss of this intricate knowledge following the decline of Hellenistic science was catastrophic. It was not merely a tool that vanished, but an entire school of thought, a way of seeing mechanics as a language for both utility and wonder. That profound break in continuity left a void that would take over 1,000 years to fill. And as we move from the controlled waters of a clock to the open sea, we find that same pattern of brilliant insight and devastating loss guiding ancient travelers across trackless oceans. The open ocean presents a navigator's nightmare, a world of shifting gray where sky and sea become one. For the Vikings, crossing the North Atlantic to reach Iceland, Greenland, and even the coast of North America meant sailing for days or weeks without a visible horizon sun. Their sagas speak of a tool that defied this gloom, the solarstein or sunstone. While no archaeological example has been found with a label declaring its purpose, a compelling candidate exists in the natural world, Icelandic spar. This remarkable crystal is a form of calcite that possesses a unique optical property. It polarizes light. When you hold a piece of this clear, rhomboid crystal up to the sky and rotate it, something extraordinary happens. Even under thick, uniform cloud cover, the crystal will appear to change in brightness and clarity. At a specific orientation, it becomes dark, while at another, it grows noticeably lighter. This shift reveals the polarization pattern of the sky, an invisible map that points directly to the sun's position, even when the sun itself is completely hidden. A skilled navigator could theoretically use two such stones, taking bearings and triangulating the sun's azimuth with startling accuracy. Experiments using replicas have confirmed this method works, not just under cloud, but during the long twilight of northern summers, potentially extending the navigational day. This was not technology born from theory, but from desperate necessity and generations of sharp-eyed observation. It represents a parallel, almost instinctual path of innovation, a deep environmental literacy written not in books but in the practiced hands of a navigator reading the sky through a crystal. The knowledge was an oral, empirical tradition, a secret of the sea that died with the last masters of the technique. It shows us that advanced understanding can wear the humble face of a found stone, a tool that gave one culture a crucial edge long before the magnetic compass became a reliable fixture on European ships. This mastery of natural forces for guidance finds a fascinating echo in a much more personal artifact, one that transformed a simple item of adornment into a private world of mechanical wonder. Heron of Alexandria invited his audience to a spectacle of pure imagination made real. In the 1st century of the Common Era, within the scholarly halls of that great city, he unveiled a theater of wonders no larger than a cabinet. This was no static model, but a fully automated stage, powered by nothing more than a falling weight, a rotating drum, and a labyrinth of strings and gears hidden within its base. At the signal, the performance would begin on its own. Tiny doors would swing open on hidden pivots. Wooden figures of gods and heroes would glide across the miniature stage, enacting scenes from myth. Sound might be provided by grains of millet or lead shot trickling onto a hidden drum, mimicking the roar of thunder or the crash of waves. Heron did not keep these secrets. He meticulously documented the engineering behind them in his work titled Automata. These devices were profound philosophical demonstrations. They explored the very principles of cause and effect, of how simple, predictable inputs, like a weight descending a cord wrapped around an axle, could be translated through clever mechanics into complex, seemingly lifelike outputs. This was an active exploration of programmable machines, a tangible investigation into the boundary between crafted object and simulated life. The automatic theater was not a child's toy. It was a serious intellectual pursuit, a fusion of art and cutting-edge technology that asked deep questions about creation and control. And then, like so many flashes of genius from that era, the tradition faded. The intricate knowledge required to design such synchronicity of movement was not built upon, it was shelved. The concept of complex automata for entertainment and wonder would lie dormant, a forgotten seed, for over 1,500 years until it was unearthed and reborn in the sketchbooks of Renaissance engineers like Leonardo da Vinci. This ancient desire to mimic life through mechanics, however, was not unique to the Greeks. A far older and more mysterious tradition of automated figures points to a much deeper and more spiritual origin. Buried within the royal treasures of an Assyrian king lay a small, unassuming piece of polished rock crystal, discovered in the palace of Nimrud and dating to the 8th century before the Common Era. The Nimrud Lens is a palm-sized oval, meticulously ground with one flat face and one convex, gently bulging outward. To the modern eye, its purpose is instantly recognizable. It magnifies. Held at the right distance, it can make small details appear larger, and if angled toward the sun, it can concentrate light into a fierce, burning point. Yet this simple fact places it in a profound historical vacuum. Was it a decorative piece for furniture, a burning lens to start fires, a tool for an artisan engraving intricate seals, or perhaps an aid for an elder with failing eyesight? The truth is, we cannot be certain. What is undeniable is the skill it represents. Shaping a brittle material like rock crystal into such a precise optical form requires remarkable lapidary technique and patience. The Assyrians were masters of fine detail, creating breathtaking reliefs and minute cylinder seals, work that would certainly benefit from a magnifying aid. If this lens was used intentionally for its optical properties, it represents a staggering precognition of a technology whose time had not yet come. The earliest known corrective lenses, the reading stones of the medieval period, do not appear for another 1,700 years. The Nimrud lens is not an invention in a lineage, it is a brilliant, isolated spark. It embodies the prototype, a concept grasped and shaped for a specific, perhaps even singular purpose within a royal workshop, but one that never ignited a broader optical revolution. It lacked the supporting ecosystem, the glassmakers, the theorists, and the widespread need that would later make eyeglasses a transformative technology. This single piece of crystal is a quiet testament to how an idea can be born, held in the hand, and then set aside, its potential lying dormant for centuries. From this intimate artifact of focused vision, our perspective now widens dramatically to an entire city where knowledge itself was not held in a hand, but carved into the bones of the earth. The desire to capture and replicate the world through mechanics finds its ultimate expression in the need to communicate. In the ancient palace of Phaistos on the island of Crete, archaeologists unearthed a small, fired clay disc, roughly the size of a modern dinner plate. Dated to around 1,700 years before the Common Era, this object is unlike anything else from the Minoan world. Both of its faces are covered in a tight, clockwise spiral of tiny, intricate symbols, 241 impressions in total, depicting everything from human heads and birds to shields and flowers. The mystery is not just in what it says, for the script remains completely undeciphered to this day. The true shock lies in how it was made. Each symbol was not carved or painted by hand. They were stamped into the soft clay using individual pre-formed seals like a set of tiny punches. This is, without question, an example of movable type printing, a technology for reproducing written information. And that fact sends a tremor through the conventional timeline of innovation. This method of printing does not appear again in Europe until Johannes Gutenberg's press in the 15th century, a gap of over 3,000 years. Think about that scale of forgetting. The Phaistos Disc represents a brilliant, isolated spark of a revolutionary idea. Someone in Bronze Age Crete conceived of a system to efficiently stamp out a message, to replicate symbols with perfect consistency. Yet this technique seemingly lived and died with this single, enigmatic object. Was it a hymn to a goddess, an administrative record, the rules of a sacred game? We may never know its purpose, but its very existence forces a difficult question. Why did this obvious, labor-saving method not catch on? Why was it not used for palace inventories or royal decrees? The answer may lie in its very uniqueness. Perhaps it was the proprietary technology of a single workshop, a secret art that died with its maker. Or maybe the complex Minoan script, primarily written by hand on clay tablets, was simply too established to be disrupted by a novel, if brilliant, technique. The disc stands as a monument to a path not taken, a premature invention that failed to ignite the communication revolution it logically should have. It shows that a technology can be conceptually born centuries, even millennia, before the social and economic conditions are ready to nurture it into widespread use. This solitary attempt to stamp meaning into clay finds a profound contrast in another ancient device, one designed not to broadcast a message to people, but to listen for a message from the heavens. The Minoan disc's silent, stamped symbols could not predict the tremors that would one day shake their world, but in a different imperial court over 1,000 years later, a scientist built a machine that could. In the year 132 of the Common Era, the brilliant polymath Zhang Heng presented the Han Emperor with a device of breathtaking ambition, the world's first seismoscope. It was a large, ornate bronze vessel, perhaps 6 feet in diameter, adorned around its circumference with 8 dragon heads. Each dragon held a bronze ball loosely in its jaws, and directly below each dragon, with mouths upturned, sat 8 corresponding bronze frogs. The principle was elegant in its reported design. Inside the vessel, modern reconstructions suggest, hung a carefully balanced pendulum. When a seismic wave from a distant earthquake reached the capital, it would cause the pendulum to swing, even if the tremor was too faint for human senses to detect. This motion would trigger a lever mechanism inside one of the 8 directional dragons, causing it to release its ball. The ball would clatter into the waiting frog's mouth below, producing both a sound and a clear visual signal. The direction from which the earthquake came was indicated by which dragon had released its prize. The historical records claim astonishing success. On one occasion, a dragon facing west dropped its ball, though no tremor was felt in the capital. Days later, a messenger arrived from a region hundreds of miles to the west, reporting a major earthquake. The device had detected what people could not, a scientific triumph that must have seemed like magic. The exact internal mechanism remains a subject of passionate debate and modern engineering challenge. Could a pendulum sensitive enough to detect such distant quakes also be stable enough not to be triggered by the rumble of a passing cart or a gust of wind? Scholars and engineers have proposed various ingenious solutions involving delicate linkages, inertial masses, or even a system of suspended weights. The fact that we are still trying to reverse engineer it today is a testament to its sophistication. Zhang Heng's seismoscope was far more than a clever toy. It represents the formal birth of instrumental geophysics, a deliberate move from simply experiencing natural disasters to systematically observing and measuring them. This was technology in service of the state, a tool for empire management, allowing the court to send aid and assess damage in distant provinces with unprecedented speed. It marks a profound intersection of mechanical ingenuity, bureaucratic need, and pure scientific curiosity, a tradition in ancient China that would produce many such independent peaks of innovation. Here was a civilization not waiting for knowledge to arrive, but actively building machines to pull secrets from the very earth itself. And as one dragon's mouth opened to the tremors below, another culture was perfecting a device to read the silent, steady motions of the cosmos above. That same desire to map the invisible forces of the earth found its mirror in a quest to chart the heavens. Carved into the stone ceiling of the Temple of Hathor at Dendera, a sprawling bas-relief captures the night sky in breathtaking detail. This is the Dendera Zodiac, a celestial map created around 50 years before the Common Era, and it is far more than a decorative pattern. It is a complex and accurate snapshot of the constellations, including the familiar figures of the zodiac, all framed within the rich symbolic language of ancient Egyptian cosmology. The precision is startling. The positions of the planets, the path of the sun, and the constellations are not randomly arranged. They reflect a deep, accumulated knowledge of astronomical cycles. This was not the work of a single artist's imagination, but the culmination of generations, perhaps centuries, of meticulous observation. To achieve such a faithful representation required more than just looking up. It implies the use of specialized tools, now lost to time, for measuring angles and tracking the slow drift of stars across millennia. Think of it as the stone printout from a sophisticated data set, the final artistic expression of a long-running scientific project. This artifact delivers a powerful challenge to a narrow historical narrative. It demonstrates that detailed cosmic cartography, a pinnacle of human intellectual achievement, was reached independently by different cultures, each using their own unique symbols and methods. The Egyptians did not need Greek or Babylonian models to understand the sky. They developed their own profound system. The zodiac itself, often thought of as a purely Western astrological tradition, is here integrated seamlessly into an older Egyptian vision of the cosmos, a meeting of astronomical knowledge across cultures. The real mystery of the Dendera Zodiac lies not in what it shows, but in what it silently implies is missing. The relief is the preserved knowledge, the final report. The observatories, the sighting tubes, the star charts and calculating tools that made it possible have all turned to dust. It is a permanent reminder that our understanding of ancient science is often based on the durable fragments that survive, while the delicate instruments of discovery vanish. This magnificent stone map forces us to ask, what other tools for measuring the universe have we simply lost? From this static, glorious snapshot of the cosmos, our journey now turns to a culture that sought not just to map the heavens, but to build a dynamic, working model of its very machinery. The cosmos mapped in stone at Dendera was a silent, beautiful record, but a philosopher in Rhodes sought to bring that same cosmos to life, to hold its turning machinery in his hands. In the 1st century before the Common Era, Posidonius constructed a device that Cicero would later describe with awe, a mechanical sphere that modeled the heavens themselves. This was an orrery, a working replica of the celestial sphere. likely driven by an intricate system of gears much like the Antikythera Mechanism. Picture a bronze globe within which delicate mechanisms turn to simulate the wandering paths of the planets, the phases of the moon, and the steady journey of the sun through the zodiac. This was not a tool for calculation but for comprehension. It transformed the abstract mathematical theories of Greek astronomy into a tangible, moving reality one could observe and explain. For students and philosophers, it served as the ultimate pedagogical device, making the complex clockwork of the universe visually immediate and undeniable. In the hands of an elite teacher, it could illustrate celestial order, demonstrate the causes of eclipses, or even, for those who believed, suggest the astrological influences of planetary alignments. The creation of such a device represents a breathtaking synthesis of disciplines. It required decades of accumulated observational data to get the planetary periods correct. It demanded a deep geometric understanding to translate those cycles into physical gear ratios, and it called for the highest level of precision metalworking to craft gears small and strong enough to mesh smoothly within a confined space. Posidonius' sphere was a pinnacle of integrative knowledge, a meeting point of the mind and the hand, and then, like a delicate clock left unwound, the tradition that produced it gradually stilled. The political and social instability that washed over the Mediterranean world fragmented the schools and workshops that sustained this synthesis. The specific knowledge of how to design and build such illustrative models became scattered, then rare, and then essentially lost. The drive to create a working model of reality did not disappear, but it was forced to start over from fragments and memories more than 1,000 years later. This profound loss of illustrative technology finds a curious parallel in a discovery from a very different context, where the goal was not to model the grand cosmos, but to achieve a perfect miniature stillness. The stillness of a philosopher's mechanical sphere finds a stark and deeply human contrast in a surgeon's kit, sealed for centuries under volcanic ash. Within the ruins of Pompeii, archaeologists uncovered a collection of bronze and iron instruments that belonged to a Roman medical practitioner. These were not the crude tools of a battlefield butcher, but a refined and specialized toolkit, a testament to a sophisticated approach to healing the body. Here were finely balanced scalpels with replaceable steel blades, delicate probes, bone levers, and forceps of various designs for specific tasks. Among the most striking is the vaginal speculum, a device of elegant and functional design. It featured two hinged blades that could be gently opened and locked into position using a finely threaded screw mechanism, allowing for internal examination with a degree of control and minimal trauma. The logic of its design, its understanding of leverage and patient comfort, is so advanced that similar instruments would not see fundamental improvement until the 19th century. This collection shatters the simplistic notion of ancient medicine as a realm of mere superstition and guesswork. It reveals a parallel track of highly developed mechanical ingenuity applied directly to the human form, born from generations of empirical practice, careful observation, and likely a surprising amount of anatomical knowledge gained from surgery and dissection. The tragedy of Pompeii preserved these tools in a single, catastrophic moment, but it also symbolizes a greater loss. In the centuries following the empire's fragmentation, this instrumental sophistication faded from common use in much of Europe. The knowledge of how to craft and properly employ such specialized devices became rare, a casualty of social upheaval and the breakdown of complex trade and educational networks. This regression was not uniform, it was selective, affecting the delicate arts of surgery far more deeply than, say, the construction of simple plows or water wheels. It is a sobering reminder that technological progress is not a single rising tide, but a mosaic of individual crafts, any of which can be washed away by the currents of time. While these tools were crafted to mend the physical form, Another ancient artifact suggests a different kind of preparation, one aimed not at the body, but at the inner landscape of the mind. A surgeon's precision with metal finds its echo in an artist's mastery over stone. Deep in the jungles of Mesoamerica, the Maya crafted objects that defy simple categorization, the so-called eccentric flints. These are not the practical spear points or cutting blades we typically associate with stone tools. Fashioned from brittle chert or volcanic obsidian between 600 and 900 years of the Common Era, they are intricate, often symmetrical sculptures chipped into the forms of gods, serpents, scorpions, or complex geometric patterns. To hold one is to hold a paradox, a piece of stone technology pushed to its absolute limit for a purpose that was purely symbolic. The manufacturing process was an exercise in controlled tension and breathtaking risk. Using a technique called pressure flaking, a master artisan would use a pointed tool of antler or hardwood to apply precise, incremental pressure along the edge of the stone blank. With each tiny click, a sliver of material would shear away. There was no room for error, no way to glue a piece back on. A single misplaced tap or an unseen flaw in the material would cause the entire piece to shatter into worthless fragments, wasting perhaps days of meticulous work. This was lithic engineering at its most refined, a high-tech craft of the ancient world. These flints challenge a deeply ingrained modern bias, the idea that technological progress is always and only about increasing efficiency, utility, or material comfort. For the Maya, the pinnacle of their stone working skill was not directed toward a better plow or a sharper axe. It was channeled into the creation of objects of ritual power and spiritual significance. They were likely used in ceremonies, perhaps as offerings, as emblems of status, or as sacred objects believed to hold the essence of the deities they depicted. The eccentric flint represents a different kind of progress, one measured in cultural meaning and symbolic complexity rather than mechanical advantage. Their existence implies a highly specialized artisan class, individuals who spent a lifetime perfecting a secretive, sacred craft. The knowledge was not written in codices, it was stored in the muscle memory of the hands, passed from master to apprentice through careful observation and practice. When the classic Maya civilization underwent its profound transformation, when the great ceremonial centers were gradually abandoned, this fragile, embodied knowledge evaporated. The ability to speak to the gods through such impossible stone simply vanished from the world. This fusion of supreme technical skill with deep spiritual purpose shows that a society's technological energy can flow in many directions, not just the practical ones we might expect. And while the Maya were perfecting the art of sacred stone on another continent, a different kind of precision was being achieved in metal, not for the gods but for the meticulous measurement of the mundane world. That mastery of stone and metal for spiritual expression finds a powerful, practical counterpart in the highlands of East Africa. Scattered across what is now Tanzania, the earth holds the remnants of tall, conical clay furnaces, silent monuments to a forgotten industrial revolution. Built by the Haya people, these structures were not for pottery or simple smelting. They were sophisticated steelmaking factories, operating centuries ago with a technique that would not be matched in the West for generations. Archaeologists and metallurgists studying these sites made a stunning discovery. Through a brilliant preheating technique, these furnaces could achieve internal temperatures exceeding 1,800 degrees Celsius, hot enough to produce high-carbon steel in a single, continuous operation. The innovation was in the design. A forced draft system, likely using bellows, fed air into a carefully prepared charge of iron ore and charcoal. The furnace's tall, conical shape created a natural chimney effect, superheating the air before it even reached the reaction chamber. This preheated blast was the key, a principle of thermodynamic efficiency that European ironmakers would not systematically employ until the 19th century. The result was a direct conversion of ore into quality steel, a material stronger and more versatile than wrought iron. This indigenous African technology may stretch back over 2,000 years, a timeline that radically reshapes the map of ancient innovation. It dismantles completely the outdated and persistent narrative that advanced metallurgy was an exclusive achievement of Eurasian civilizations. Here was a society that developed a superior chemical and thermal process independently, driven by local needs and a deep understanding of their immediate environment. They used the resources at hand to solve the problems before them, achieving a technical peak on their own terms. These furnaces were not isolated machines, they were nodes in a holistic system. The knowledge was communal, passed down through generations, integrated into the social and economic fabric of the community. This was a different paradigm of progress, one where technological sophistication was measured not by conquest or monument building, but by sustainable mastery over material to serve a community's needs. Their silent forms remind us that the history of invention is not a single race with one finish line, but a vast global tapestry of brilliant local solutions, many of which were never recorded in the chronicles that came to define the mainstream story. And just as these furnaces measured the heat needed to transform rock into steel, another ancient society perfected the art of measuring the earth itself, turning the very landscape into a tool of astonishing precision. The precise lines of those ancient steel furnaces found their echo in the straight, unwavering roads that stitched an empire together. In the hands of a Roman land surveyor, the key to this geometric mastery was a tool of elegant simplicity, the Groma. Picture a tall staff planted firmly in the earth. At its top, a horizontal cross pivoted, and from the end of each of its four arms, a fine cord dangled, each weighted with a heavy plumb bob. To the untrained eye, it might look like a child's toy. To the Roman engineer, it was the instrument that laid the foundation of their world. By sighting along two opposing pairs of these perfectly vertical cords, the surveyor could establish a flawless straight line, or by turning the cross 90 degrees, a perfect right angle. This was the bedrock of Roman order. With a Groma, a team could mark out the grid of a new military camp in a matter of hours, its streets intersecting at precise 90-degree angles for optimal defense and control. They could carve the landscape into perfect squares of farmland, a process called centuriation, assigning plots to veterans with mathematical fairness. And most famously, they could plot the relentless, straight courses of their roads, often ignoring gentle contours in the land to maintain that iconic directness. The Groma's genius was not in its complexity, but in its systematic, repeatable reliability. It transformed the abstract concepts of geometry into a physical, field-ready process that could be taught, replicated, and executed across 3 continents. This simple tool demonstrates a profound truth about technological progress, that transformative power often lies not in a flashy, singular invention, but in the widespread, disciplined application of a fundamentally sound idea. The legacy of the Groma is not stored in a museum case. It is permanently etched into the geography of Europe, visible in the property lines of old farms and the arrow-straight paths of ancient roads still followed today. It reminds us that some of history's most enduring innovations are those that organize space itself. But if the Romans could so masterfully measure and divide the land, how did another great civilization grapple with the far more fluid and elusive challenge of measuring time itself? The Roman surveyor's Groma measured the land with geometric certainty, but the passage of time remained an elusive river to chart. For the ancient Chinese, this challenge was met not just with observation, but with a mechanical marvel designed to conquer confusion itself, the legendary South-Pointing Chariot. Historical texts from the 3rd century of the Common Era describe a ceremonial vehicle used in imperial processions, atop which stood a small carved figure. Its outstretched arm, incredibly, always pointed toward the south, no matter how many turns the chariot made along winding palace roads or through crowded streets. This was no spiritual trick, it was a triumph of pure mechanical computation. The figure was not guided by a lodestone, but by an intricate system of gears connected directly to the chariot's wheels. At its heart was a differential gear assembly, a set of interlocking gears that calculated the difference in rotation between the two wheels. When the chariot turned left, the right wheel would rotate farther than the left. The differential gears would translate this difference into a compensating rotation in the opposite direction for the figure on top, keeping it perfectly oriented to its original heading. It was, in essence, a mechanical analog computer performing dead reckoning, a feat of engineering that would not be replicated in the West until the differential gear was reinvented for modern automobiles in the 19th century. While no original chariot survives, numerous detailed reconstructions based on ancient manuals have proven the design not only feasible but brilliantly effective. This artifact represents more than a clever toy. It symbolizes a distinct and parallel path of innovation. Chinese mechanical genius was often channeled toward solving problems of statecraft, ceremony, and cosmological harmony. The South-Pointing Chariot was a moving testament to imperial order and navigational certainty, a symbol that the emperor's court, no matter how complex its maneuvers, was always correctly aligned with the heavens. It showcases a tradition of mechanical thinking that developed in profound isolation, reaching conceptual heights that were later reached independently elsewhere. This grand, ceremonial application of gears to maintain direction finds a fascinating, intimate counterpart in a much smaller object, one that applied a similar principle of orientation not to a chariot but to the human hand. The South-Pointing Chariot ensured imperial order through mechanical computation, but a far smaller Roman artifact applied similar ingenuity to a more personal arena, the friendly competition of a board game. Within the excavated remains of a 4th century Roman fort or villa, archaeologists have occasionally found a curious bronze object, a hollow, rectangular tower just a few inches tall. Its top is a wide funnel and its base is an open chute. This is a turricular, a dice tower, and its purpose was both brilliantly simple and socially profound. In a world where dice were often hand-carved from bone or ivory and could be subtly weighted, the temptation to cheat in a high-stakes game was ever present. The turricular was the elegant solution. A player would drop their die into the funnel at the top. Inside the tower, a series of staggered, slanted baffles like a miniature, chaotic staircase forced the tumbling cube to bounce and ricochet in an unpredictable cascade before it finally emerged from the bottom chute. This mechanical process, using the principle of randomization through chaotic deflection, removed the human hand from the final throw, guaranteeing a fair, unbiased result. It was a physical random number generator, centuries before the term existed. This small device speaks volumes about the Roman world. It tells us that leisure and gaming were serious, sophisticated pursuits, important enough to warrant specialized anti-cheating technology. It reveals how mechanical thinking had permeated every layer of society, from the grand engineering of aqueducts down to the simple desire for an honest game among friends. The dice tower is a microcosm of applied physics in daily life, a testament to the Roman propensity for creating clever, practical devices to enforce social order and ensure pleasure. It reminds us that technology is not always about monumental tasks, but often about solving the small, human-scale problems of trust and fairness. Yet while the Romans were perfecting devices to ensure random chance in play, another ancient culture was perfecting a device to eliminate chance from one of life's most critical and delicate tasks. The desire for fairness in a game of chance reveals a culture thinking deeply about mechanics, but the true test of engineering lay in moving the immovable. High on the scaffolding of a half-built Roman temple, the air would have thrummed with a steady, rhythmic creaking, the sound of a machine transforming human effort into monumental force. This was the Polyspaston, the Roman portable crane, a wooden masterpiece of leverage and ingenuity. Far from a simple hoist, it was a system, a brilliant orchestration of rope, wood, and disciplined labor. At its heart was the compound pulley, a nest of wheels that multiplied strength, allowing a rope to be pulled many times its length to lift a load a much shorter distance with dramatically reduced force. But the Romans added a crucial innovation, the human-powered treadmill wheel. Picture a large, hollow wooden wheel, like a giant hamster wheel, mounted horizontally within the crane's frame. A team of men would walk steadily inside it, their collective weight and motion turning the axle. This axle, acting as a winch, would then reel in the rope threaded through the complex pulley block above. Through this elegant arrangement, a small crew of perhaps 5 or 6 men could, with their steady, synchronized steps, lift limestone blocks weighing several tons to dizzying heights. The architect Vitruvius described its mechanics with clear admiration, and stone reliefs from tombs show these cranes in action, their silhouettes etched against half-finished columns. This was not a secret technology, but a standardized, repeatable solution. The Polyspaston was the workhorse behind the Roman architectural miracle, enabling the rapid, precise construction of aqueducts, amphitheaters, and soaring temple porticos. It represents the ultimate systematization of mechanical advantage, a democratization of superhuman strength available to any well-trained engineering corps across the empire. Its legacy is one of astonishing longevity. The core principles of its design, the treadmill, the compound pulley, the wooden boom, remain the foundation of all construction cranes for over 1,500 years, only finally being supplanted by the steam-powered winch. This machine shows that a technology can reach a state of such perfected, functional elegance that it becomes a permanent part of the human toolkit, a peak of pre-industrial engineering that was never improved upon, only eventually replaced by a different source of power. With such mastery over lifting stone from the quarried earth, we must now ask, how did they first extract those colossal blocks from their ancient beds? The precision of the Roman crane in lifting stone is only matched by the mystery of how that stone was first cut. Within the shadow of the Great Pyramid at Giza, a small, unassuming piece of granite holds a startling secret. It is a drilled core, a cylindrical sample extracted from a massive block during the pyramid's construction over 4,500 years ago. To the untrained eye, it is just a rod of stone, but a closer look reveals its true marvel. The surface is marked with perfectly uniform spiral grooves like the threads of a screw. These grooves are not random scratches, they are the preserved record of a high-speed drilling process. The spacing of these spirals tells a dramatic story. Experiments by engineers and archaeologists have shown that to create such a consistent, deep groove in granite, a tubular drill made of copper would have been used, loaded with a continuous flow of an abrasive like quartz sand. As the drill was turned, perhaps by a bow or a team of workers, the hard sand particles embedded themselves in the softer copper, creating a cutting edge that slowly, relentlessly, ground its way through the rock. The consistent groove spacing indicates a feed rate, the speed at which the drill advanced into the stone, that is remarkably efficient, even by modern standards for hand-powered tools. This was not a crude bashing away at the rock. This was a controlled, repeatable machining operation. It required a sophisticated understanding of rotational motion, the physics of abrasion, and the application of sustained downward force. The artisans knew that the tool material, copper, could be softer than the granite, so long as it carried a medium, the sand, that was harder. This principle of using a loose abrasive with a carrier tool is a cornerstone of precision machining, and here it was in full practice millennia ago. These drill cores dismantle the persistent myth of pyramid construction as a story of limitless slave labor and brute force alone. They point instead to a highly specialized, guild-based industry of master craftsmen. These were the ancient world's machinists, men who possessed and guarded a body of empirical knowledge about materials and processes, knowledge so valuable it was likely passed only from father to son within closed workshops. This was a technology born from and sustained by the demand for perfection in monumental sacred architecture. When the age of the great pyramid builders passed, when the pharaoh's ambitions turned to less colossal projects, the concentrated need for such extreme precision faded. The specialized knowledge so tightly held within a small artisan class gradually dissipated. The ability to drill granite with such flawless consistency became a lost art, a peak of material science that would not be systematically rediscovered and improved upon until the Industrial Revolution. This quiet piece of granite proves that the ancient world possessed not just strength, but a science of the workshop, a forgotten industry of precision. And if they could shape stone with such exacting control, what does that imply about their mastery over a more malleable but equally demanding material? The same mastery over materials that shaped granite could be forged into a weapon of both war and identity. When a Frankish warrior of the 5th century drew his blade, he revealed more than a tool for battle. He revealed a captured storm of light and shadow. The surface of a Merovingian pattern-welded sword is a hypnotic dance of rippling lines, a wood grain pattern flowing through the steel. This was no simple decoration painted on. It was the very soul of the blade, forged in from the very beginning. The smith began with multiple rods of iron and steel, each with different carbon contents. These rods were bundled together, heated to a brilliant, precise orange in the forge, and then hammer-welded into a single, solid billet. But the true artistry came next. This billet was then twisted like a candy cane, sometimes multiple times, and then folded and welded again, over and over. This created a laminated structure, hundreds of microscopic layers fused into one. Finally, the blade was ground and polished, and when acid, perhaps from fermented fruit or vinegar, was applied, it etched the surface. The different metals reacted at different rates, revealing that mesmerizing, swirling pattern for all to see. This was metallurgical alchemy with a profoundly practical purpose. The technique created a blade that was a masterpiece of material optimization. The lower carbon iron layers provided a resilient, flexible spine that could absorb the shock of a brutal parry without snapping. The higher carbon steel layers, concentrated at the edge, could be honed to a razor sharpness that would hold its bite. It was the best of both worlds in a single weapon, a solution born from limited resources and limitless ingenuity. Achieving this required an empirical, almost intuitive science. The smith had to control temperatures by the color of the glow in his charcoal fire, understand chemistry by the sparks that flew from his hammer, and judge timing by years of ingrained instinct. Each sword was a unique signature, its pattern impossible to perfectly replicate, making it a deeply personal emblem of its owner's status and lineage. In the turbulent centuries after Rome's fall, this technology represents not a collapse of knowledge, but its brilliant, focused adaptation. Innovation did not cease, it specialized, flowing into the crafts that defined the new warrior aristocracies of Europe. The pattern-welded sword is a defiant statement that even in an age of fracture, the human drive to perfect, to beautify, and to solve material problems with fire and skill burned brighter than ever. This fusion of art and empirical science in the smithy finds a fascinating parallel in a very different workshop, where the goal was not to shape metal for conflict, but to manipulate light for understanding. The same fire that danced in the smith's forge could be harnessed as a weapon of apocalyptic terror upon the sea. For an Arab sailor facing the Byzantine navy, the most horrifying sight was not an enemy ship, but the strange bronze tube mounted on its prow and the jet of liquid flame that erupted from it. This was Greek fire, and the siphon that delivered it was a state secret so potent it sustained an empire for centuries. The terror it inspired was absolute, for this was no ordinary flame. It clung to the water's surface, burning with a ferocious intensity that water could not quench, only spreading the inferno. While its exact chemical recipe died with the Byzantine emperors, likely a volatile mixture of crude oil, pine resin, and other secret ingredients, the delivery system itself was a marvel of military engineering. To project this unstable, sticky liquid across the waves required more than a torch and a pot. It demanded a sophisticated pressurized system, a bronze pump and siphon capable of building and releasing immense force, with precisely machined valves to control the flow and prevent a catastrophic backfire that would consume the ship that carried it. The operators, protected behind heavy shields, would work the pump, forcing the concoction through a heated bronze tube that ignited it as it sprayed toward the enemy. This was a weapon system integrating advanced chemistry, fluid mechanics, metallurgy, and tactical deployment. It gave the outnumbered Byzantine fleet an insurmountable technological edge, turning the tide of countless naval engagements and securing the empire's survival during its most desperate centuries. Yet this supreme advantage carried within it the seeds of its own oblivion. The secret was guarded with paranoid intensity, known only to a handful of artisans and the imperial family. This extreme secrecy meant the knowledge was never diffused, never written down in manuals that could survive the empire's final collapse. When Constantinople finally fell, the art of crafting both the liquid and the machine that hurled it vanished utterly. It stands as the ultimate example of a technology so powerful, so closely held, that it became a fragile heirloom rather than a stepping stone for progress. Its brilliant flash illuminated the pages of history, and then it was gone, leaving only echoes of its thunder on the water. From this terrifying, lost application of pressure and flame, we find a profound shift to a device that harnessed a gentle, constant force for an entirely different purpose, the quiet measurement of time's peaceful passage. That terrifying liquid fire was a weapon of pure defense, a secret held to protect an empire. In the heart of a different empire, a towering machine was built not for war, but to reveal the peaceful, predictable order of the cosmos itself. In the year 1092 of the Common Era, in the northern Song dynasty capital of Kaifeng, chief astronomer Su Song completed a structure that must have seemed like a living myth. It was a clock tower over 30 feet tall, a symphony of bronze, wood, and flowing water known as the astronomical clock tower. This was not a timepiece you kept on a shelf. It was a public monument to imperial power and celestial harmony, a mechanical universe in miniature that anyone in the capital could witness. Its beating heart was a massive water wheel, but this wheel did not turn millstones. It was regulated by a brilliant invention, the water wheel escapement mechanism. Imagine a precise, intermittent catch and release. As water filled a series of buckets on the wheel's rim, the weight would eventually trip a lever, allowing the wheel to rotate just one precise step before being locked again. This ingenious device transformed the continuous flow of water into a measured, tick-tock motion, providing the steady, controlled power needed to drive the entire complex machine. And what a machine it was! This single tower housed multiple functions in perfect synchrony. At the top, an elaborate armillary sphere for mapping star positions turned automatically to match the sky. Inside, a celestial globe rotated to show the constellations, and on the front, a procession of animated mannequins emerged from behind doors at set intervals, ringing bells and holding tablets to announce the hour. It was an observatory, a planetarium, and a public clock, all driven by one integrated hydraulic system. Su Song did something remarkable for his time. he wrote a detailed, illustrated treatise explaining the tower's construction down to the individual gear teeth. This document survives, allowing historians and engineers to fully appreciate its sophistication. The escapement mechanism was a landmark achievement, a critical conceptual leap toward fully mechanical timekeeping. Yet here lies the profound puzzle. This brilliant Chinese innovation did not spark a continent-wide revolution in clockmaking. The knowledge, while documented, remained largely within the empire's borders. Centuries later, European clockmakers independently developed the verge escapement, the cornerstone of their own mechanical clock tradition. The Tower of Su Song stands as a majestic, isolated peak. It represents a parallel path of technological development that reached a stunning height of integration and public spectacle, a testament to a culture that saw the cosmos as a clockwork system to be mirrored on Earth. Its fate reminds us that a pinnacle achievement, no matter how advanced, can remain a cultural monument rather than a global catalyst. The journey from this public, cosmic machine now turns inward to a private device of pure intellect, a tool for calculation that could be held in one's hand. The quiet calculation of an abacus required a steady hand, but the sustenance of an empire demanded a different kind of daily grind. In the shadow of Mount Vesuvius, preserved in the ashen stillness of a bakery in Pompeii, stand the heavy, silent sentinels of Roman industry. These are the Pompeian mills, massive hourglass-shaped stones carved from rough lava rock, each one taller than a man. Their design is a masterpiece of brutal efficiency. Two conical stones fit together, the upper one hollowed into a funnel-like hopper. Grain poured into the top would be caught between the grinding surfaces as the upper stone was rotated, either by the relentless push of a slave walking in a circle or by the blind, plodding strength of a donkey. The genius lay in the rotary motion itself, a significant leap from the back and forth rocking of the older saddle quern. This continuous circular grind was not only faster, it applied force more evenly, producing a finer, more consistent flour. The central iron spindle that aligned the stones and the cleverly angled grinding surfaces maximized the transfer of animal or human power into useful work. This was not a flashy invention for the elite. It was the humming engine of everyday life, a technology focused squarely on the most fundamental human need, food. The standardization of this design across the vast Roman world is its own quiet marvel. From Britain to Egypt, the same basic form of the hourglass mill appeared, a testament to how a truly effective mechanical solution, once proven, could ripple out to create a common technological baseline for an entire civilization. This widespread adoption had a cumulative impact that is easy to overlook. By making flour production more efficient, these mills freed up labor, supported larger urban populations, and underpinned the complex supply chains that fed both legions and citizens. They remind us that the bedrock of ancient advancement was often this gritty, unglamorous work of perfecting the machines of subsistence. While one mill ground grain to feed a city, another ingenious Roman device was designed to protect a different kind of essential harvest, preserving the bounty of summer through the barren winter months. That same ingenuity that ground grain to feed a city was also directed toward a far more precious and fragile resource, water itself. In the heart of the Iranian desert, where the sun bleaches the sky and the ground cracks with thirst, an ancient civilization performed a miracle of quiet persistence. They did not build towering aqueducts of stone, but instead, they learned to listen to the earth and to walk a gentle slope for miles beneath the burning sand. This is the Qanat, a water management system so profoundly simple and effective that it sustained life for thousands of years. Imagine a gently sloping tunnel, carved entirely by hand, stretching from the foothills of a mountain range to a distant oasis or settlement. At its source, the Qanat taps into a mountain aquifer, a hidden reservoir of groundwater. The tunnel is dug with just enough of a decline, perhaps 1 meter for every kilometer, to allow gravity to pull the water along its entire length, all while keeping the channel safely underground. This was the key to its genius. By traveling beneath the surface, the precious water was shielded from the relentless evaporation of the desert sun, arriving cool and clean at its destination. But the construction of a Qanat was a monumental feat of communal engineering and deep knowledge. It began with master surveyors identifying the right aquifer and plotting the precise, almost imperceptible downward path. Teams of diggers, known as mukanis, would then sink a series of vertical shafts down to the planned tunnel depth, sometimes every 20 or 30 meters. These shafts served a dual purpose. They provided ventilation for the workers below and allowed for the removal of excavated soil. Most critically, they became permanent access points for maintenance, a lifeline for the community that depended on the water's flow. This was not a project for a single lifetime. It was an intergenerational covenant with the land. A single Qanat could run for dozens of kilometers, representing countless years of coordinated labor. The system demanded and fostered a highly specialized social structure with clear rules for water distribution, shared responsibility for cleaning the channels, and a deep respect for the delicate balance of the underground resource. This technology, dating back to the early first millennium before the Common Era, spread from Persia across North Africa to Arabia and even as far as Spain. It enabled the rise of cities and farms in landscapes that otherwise offered only hardship. The Qanat challenges a modern bias that equates advanced technology with complexity, with gears and metal and moving parts. Here was a peak of innovation that was elegantly low-tech, a brilliant application of basic principles in hydrology, surveying, and civil engineering. It was a sustainable dialogue with the environment, a system that worked with gravity and geology rather than trying to overpower them. Its legacy is one of silent endurance, a testament to the fact that some of humanity's most profound solutions are not complex machines, but intelligently designed systems for living in harmony with a challenging world. This mastery of channeling a vital resource through darkness finds a beautiful parallel in our next discovery, where the goal was not to manage water, but to capture and sculpt pure light itself. A shimmering cup of Roman glass holds a secret that changes with the light. In ordinary daylight, the 4th century Lycurgus Cup appears a solid, opaque jade green, its surface carved with a dramatic scene of the mythological king Lycurgus entangled by vines. But when a light source is placed behind it, something magical happens. The entire vessel transforms, glowing with a translucent, ethereal ruby red, as if lit from within by a captured sunset. This is not a trick of the eye or a simple pigment. It is a phenomenon called dichroism, a property achieved through what we now understand as ancient nanotechnology. The Roman glassmakers, through generations of empirical trial and error, learned to impregnate their glass with astonishingly precise amounts of colloidal gold and silver. They were not merely adding specks of metal, they were creating nanoparticles, particles so small they are measured in billionths of a meter. These particles interact with light in a specific way, scattering green wavelengths when light reflects off the surface and allowing red wavelengths to pass through when the light shines from behind. To achieve this, the artisans had to master a breathtakingly delicate alchemy. They needed to add the exact minute quantities of metal salts to the molten glass batch, then control the furnace temperature and the cooling process with absolute precision to encourage the metals to form into nanoparticles of the correct size and distribution, rather than clumping together into useless flakes. This was a high-stakes recipe where a slight error would result in a failed, cloudy batch. The Lycurgus Cup is therefore more than a beautiful artifact. It is a relic of a secretive, guild-based craft operating at the very frontier of material science. Its creators possessed a working knowledge of colloidal chemistry 1,500 years before the science existed to explain it. They were manipulating matter at a scale invisible to them, guided only by the observed results of their carefully guarded techniques. This knowledge was never formally documented in a text. It was stored in the practiced hands and guarded recipes of master artisans. When the economic and social structures that supported such luxurious, specialized crafts eroded, the secrets of how to make dichroic glass vanished from the world for over a millennium. It is a perfect, glittering example of a technological peak born from artisanal intuition, a fleeting mastery of light and matter that was held and then lost in the palm of a hand. This ancient command over an invisible force, light, finds a powerful parallel in another civilization's ambition to harness a far more visible and turbulent power, the wind itself. The silent engineering of the Qanat found its perfect partner rising high above the rooftops. In the searing heat of ancient Persian cities, a different kind of tower offered not water, but a gift of moving air. These are the Baghdad, the Windcatchers, and their design is a masterpiece of architectural intuition. They stand like sentinels, their tall, rectangular faces open to the world, but with a crucial, intelligent twist. Each tower is divided internally by thin walls, creating multiple vertical shafts. The side facing the prevailing wind is fully open at the top, ready to capture and channel the slightest breeze downward. But the true brilliance is in the other side, the leeward shafts. As the captured wind is pushed down one channel, it creates a pressure difference, pulling the stale, warm air from the rooms below up and out through the opposite shafts. This creates a continuous, gentle circulation, a breath for the building itself. The cooling effect was often enhanced by pairing the Windcatcher with a Qanat. The air, funneled from above, would be directed over the surface of a cool underground water channel or an indoor pool, picking up moisture and dropping in temperature through evaporation before whispering into the living spaces. This was a complete, integrated climate system. It required no fuel, no moving parts, no external power source beyond the wind and the physics of air and water. Its intelligence was baked into the very bricks and geometry of the home. The Baghdad represents a profound and often overlooked branch of technological progress, one focused not on conquest or industry, but on sustainable human comfort. It is a technology of harmony, a dialogue with the environment rather than a declaration of war against it. The knowledge required to build one effectively was deep and localized, understanding prevailing wind patterns, seasonal shifts, and the specific thermal properties of local materials. This was innovation measured not in horsepower, but in the quiet sigh of relief on a blistering afternoon. It shows us that a society's technological energy can be directed inward, toward refining the quality of daily life in brilliant, passive ways. This ancient art of channeling invisible currents for comfort brings us at last to our final artifact, where the goal was to channel a very personal, human current into something far more elusive, the creation of enduring sound and profound mystery. Deep in a Slovenian cave, a cave bear's thigh bone rested in the dark for millennia. Discovered at the Divj Babe site, this fragment of femur is about 60,000 years old, and it is pierced by 4 carefully aligned circular holes. To the archaeologists who unearthed it, a startling possibility emerged. This was not a random act of gnawing by a predator. The placement of the holes, their clean edges, and their alignment suggest a deliberate, crafted design. When a modern musician blows gently across one end, the bone can produce a haunting, resonant scale of notes. This is the Divj Babe flute, and if its interpretation holds, it is not merely an ancient instrument. It is a message from a mind we have long misunderstood, crafted by Neanderthal hands. The implications are profound, echoing across the entire timeline we have explored. If Neanderthals were making and playing music, they were engaging in an act of pure abstraction. Music is a technology of emotion and social bonding, a tool for creating shared experience that serves no immediate physical need like cutting or grinding. It requires foresight to shape the bone, an understanding of acoustics to space the holes, and the cognitive capacity to organize sound into patterns that carry meaning. This single artifact, a simple tube of bone, suggests that the inner lives of these ancient cousins were rich with symbolism, creativity, and a form of intelligence that expressed itself in beauty. It pushes the origin of complex musical technology back tens of thousands of years before the arrival of modern humans in Europe, challenging a narrative that reserved such cultural sophistication for our own species alone. Yet, like so many artifacts we have seen, its story is wrapped in debate. Skeptics propose the holes could be the result of a spotted hyena's bite, a natural puncture that coincidentally aligns. The controversy itself is a perfect mirror to our entire journey. The interpretation of ancient objects is never a simple matter of fact. It is a conversation between the artifact and our own assumptions, a delicate process of reasoning that forces us to question the boundaries we have drawn around intelligence, creativity, and capability in the deep past. Whether one hears the clear notes of a melody or the random marks of chance in this bone, its very existence demands a re-evaluation. It asks us to listen, not just for a possible tune, but for the echoes of a different kind of human mind, one capable of turning a functional object into a vessel for something as intangible as song. This bone flute, potentially the oldest instrument on Earth, brings our exploration of 30 mechanical marvels to a fitting close. We have witnessed water-powered factories and celestial computers, precision lenses and earthquake detectors, steel furnaces and musical bones. Each one in its own way was a peak. Each represented a flash of understanding, a local optimization, a brilliant solution to a specific problem faced by a specific people in a specific time. Some of these peaks were connected by gentle slopes of shared knowledge, but so many others stand in isolation, like mountains separated by vast valleys of forgetting. This is the pattern that emerges, not a smooth, inevitable line of progress, but a landscape of scattered, luminous summits. Human ingenuity does not march, it flickers. It sparks into brilliance where conditions are right, where need meets curiosity, and where knowledge is carefully tended. And as history's winds shift, those sparks can dim, leaving only the artifacts as silent witnesses to heights once reached and then, for a time, lost. The story of technology is not one of constant ascent. It is a story of discovery, of wonder, and of the fragile, recurring miracle of seeing a problem and daring to craft a solution, whether from bronze, stone, water, or bone. This scattered landscape of peaks and valleys is the true shape of human ingenuity. These 30 artifacts, from the cosmic clockwork of Antikythera to the silent song of a bone flute, do not trace a steady climb. They map a constellation of brilliant, isolated fires, each one a testament to what a particular culture could achieve when need, curiosity, and stability converged. Time and again, we see a society reach a stunning height of mechanical sophistication. The Greeks with their intricate gearing, the Romans with their industrial hydraulics, the Chinese with their monumental clockwork, only for that specific knowledge to later recede. It became fragmented, locked away in secret guilds, or buried entirely by social upheaval. This is not a story of linear progress, but of a sputtering engine, roaring to life with incredible power in one valley, then falling silent for centuries before the next ignition in a distant land. The comforting narrative of inevitable, cumulative advancement begins to crack under the weight of these objects. They suggest that progress is not a birthright, but a fragile achievement. It is contingent on a delicate web of conditions we often take for granted: stable institutions that fund inquiry, open networks that transmit knowledge, and educational traditions that pass the torch from one generation to the next. A single war, a famine, or a shift in political or spiritual priorities could sever that chain, leaving a masterpiece like Su Song's clock tower as a magnificent dead end rather than a stepping stone. This cyclical model forces a humbling realization. Our own technological age, for all its global connections and digital libraries, is not immune to this pattern. It asks us to value not just the flash of invention, but the often invisible, unglamorous systems that nurture, sustain, and share that spark. We must ask ourselves, what are we building today that is as brilliant and as vulnerable as the Antikythera Mechanism was in its time? And this leads to a final, compelling question. Why do these stories of lost technology hold such power over us in the modern world, an age defined by its own relentless, accelerating innovation? Perhaps it is because they are mirrors reflecting our own deepest anxieties and hopes back at us. These whispers from the past form a chorus, and its song is one of profound humility. The true lesson of these 30 artifacts is not simply that ancient people were clever. It is that they were capable of thinking in ways that completely bypass our assumptions of linear, cumulative progress. They solved problems with a creativity unbound by our modern categories, reaching for solutions that were brilliant, localized, and often startlingly unique. A Roman engineer looked at a hillside and saw a flower factory in the cascading flow of water. A Chinese astronomer envisioned a clock tower as a public model of the cosmos itself. A nameless artisan in Persia learned to cool a home not with a machine, but with the very architecture, catching the wind and guiding it over water. These were not steps on a single staircase we are all climbing. They were leaps in different directions, exploring diverse landscapes of possibility. Our current technological age, for all its globe-spanning networks and digital speed, is just one chapter in this much longer, more mysterious story. It is a chapter of remarkable consolidation and acceleration, but it is not the final word. These objects remind us that the flame of ingenuity has flickered brightly in countless places and times, often in forms we would never predict. They urge us to shed the arrogance of the present, to look at the deep past not as a primitive prelude to ourselves, but as a gallery of alternate paths, of dazzling peaks that were reached and then, for a time, left behind. Let that inspire not nostalgia, but a deeper curiosity. What problems do we face today that might be solved by a perspective we have forgotten? What knowledge are we, in our own era, taking for granted or failing to pass on? The search for lost understanding is never truly over, because every forgotten artifact is a question waiting to be asked again. I would love to hear which of these 30 marvels most reshaped your view of history. Share your thoughts in the comments below, and if you are eager to continue unraveling the profound mysteries of our shared past, be sure to subscribe. There are always more whispers waiting to be heard.